Denise Gaitsgory from Harvard, who will speak about moduli space of l-adic local systems and applications to Langlands theory.
Thank you so much for the invitation. All right, so I will first remind you what Langlands theory, classical Langlands theory says, but however, we'll do it in the function field setting where kind of it's easier to formulate. So we'll proceed as follows. So FQ will be finite field, and the geometry will be done, let me just emphasize, over its algebraic closure. Is done, well, over any algebraically closed field over FQ. Doesn't have to be FQ bar, just our algebra geometric objects are defined over FQ. And so X is a curve, smooth projective curve, again, defined over FQ. G, so reductive group. And in this case, one considers the algebra geometric object, I call it bund G. So it's the moduli stack of G bundles on the curve. So we consider it, as I said, over K, but it's defined over FQ. So one can consider the set. So it's a stack, not a scheme, but we can still, so its set of FQ points is not a set, it's a groupoid, but one can consider the set of isomorphism classes of points. So we consider bund G of FQ. So set of isomorphism classes of FQ points of bund G. And this is a set, it's infinite. And one considers functions on it with finite support. So with functions with values, let's say in QL bar. And this is, well, what in number theory is called the space of unramified automorphic functions, and we'll denote it autom. Can I repeat? The space of unramified automorphic functions. All right, so I'll first give you a caveman's version of Langlands correspondence. So cavemen have heard that, so the following slogan, that cuspidal, irreducible, automorphic representations are in bijection with irreducible representations of, so the Galois group, well, let me say more precisely, V group of X into G check. So modular conjugation. So I'm slightly deviating from my convention. So here, when I write X, I mean X over FQ. And so the difference between V group and the Galois group is that, so the Galois group of FQ bar of FQ is Z hat, and we replace it by its subgroup, which is Z. So, so that's what Caveman heard. And it's not quite precise, but it's actually true as is for GLN. So for GLN, this is true as is. And it's a theorem of Laurent-Laforgue. All right, but now, so Caveman wanted to improve on this a little bit, and they said that, well, I don't want to now explain what it means, irreducible cuspidal automorphic representations. You're just basically breaking up the space of functions on what this automorphic space into irreducibles with respect to the action of the Hecker algebra. But we want to improve slightly on that. We actually would like to describe the space of automorphic functions as is, without breaking it into irreducibles, in terms of the Langlands dual group. Well, and then, so, well, Caveman said, just wait a minute, this instead of taking these irreducible representations one by one, how about we organize them in a family? Let's try to consider, so the moduli space of representations of modular space of representations like this, of the Weil group. And let's call it log sys with respect to G check arithmetic. Arithmetic to emphasize that we are doing it over FQ, or the FQ bar. So it's an algebraic stack. Let me just jump ahead, a few minutes ahead, to say that the problem with cavemen is that they were ignorant of the fact that this modular space doesn't exist. Still, they plowed on ahead. They said, let's look at the modular space. Well, and before we took just points on it, and we took them one by one, and now we want to create a certain vector space of the modular space. They said, you know what, let's just take global functions. Sections of the structure sheaf. And so here is Caveman's Langlands conjecture. So they conjectured that just the space of automorphic, unramified automorphic functions is just isomorphic to this vector space. And so there are two, well, as I said, slight problem here is that the modular space of this doesn't exist. The amazing fact is that once we create this modular space, it will turn out that the caveman's guess is almost correct. So primitive as they were, they actually guessed almost correctly. And so the true conjecture, so correct conjecture is the following, that the automorphic space of automorphic functions is indeed global sections, but not of the structure sheaf, but of the dualizing complex. And the difference is actually significant. So if you are, so if Y is your algebraic stack, if it is a locally complete intersection, so if Y an LCI, so then, well, this dualizing sheaf is, well, it's not necessarily O, but it's a line bundle. So there's maybe not so much difference between sections of O and the line bundle, but what happens is that the stack of local system is really not LCI, and moreover, it's not a classical algebraic stack, it's a derived algebraic stack, and so the structure sheaf doesn't fit on one cohomological degree. So in fact, so these two things are really different. All right, and now, so that was the introductory part. Now I'll explain what is what. And so the first thing I'll try to explain is what is this beast, the stack of local systems. But before that, let me pause for questions.
You said that it does not exist, this log sys arithmetic doesn't exist. It does not exist as what? It certainly looks at as a stack, it's well defined.
I'm jumping back and forth in time. So it did not exist until very recently, but now it does exist.
No, but why it's naively? I mean, you have a group, you have a representation, homomorphism, modular joint action. It looks like, well, what's the problem?
This is exactly what I'll explain now. I'll explain in what sense why a naive attempt along the lines you're suggesting will not work, and then I'll explain how to correct it, how to make it work.
Okay.
That's exactly the kind of the first point I'll explain. Any more questions? All right. So So let's first recall the definition of log-sys where it actually does exist. So namely, that's the kind of usual topological context. So let's, instead of X being a curve over field of positive characteristic, let X be Riemann surface, or in fact any topological space. So I'll say what log-sys for our group G on X is in this case, but I'll mark it Betty. So that's the Betty version. So that's really an algebraic stack, and I'll now define it. But I'll define it in the way that it'll be convenient for me to generalize later. So by the way, when I talk about local systems, they have coefficients. So, and when I work in this topological context, coefficients can be, let's say, I'll take a field of characteristic 0, but arbitrary algebraically closed field of characteristic 0. Let me call it E. So it's a field of coefficients. And so in our l-adic story, E will be QL bar. So what I want to distinguish is the geometry over which, so our geometry is taking place over one field. So in this case, it's the field K, and coefficients is a different field. It's called the field called E. So, and this log-sys Betty is an algebraic stack over the field of coefficients. So, well, how do we define an object of algebraic geometry? We specify what its points are with values in affine schemes. So home from spec A to this log-sys G check Betty is the following thing. It's the groupoid of symmetric monoidal functors. Condition they are right exactly with respect to T structure, symmetric monoidal. I'm giving the Tanakian description from the category of algebraic representations of rep G check into the category of, well, locally free sheaves. Well, locally constant sheaves on X of A modules. So, in other words, for like if your group is G check is GLN, what you're doing, you're really you're considering a local system on X of free A modules of rank N. So that's what we're doing. So this target category is convenient to rewrite in the following terms, and we'll be using it later. So let me do it already. So as a category, it's actually what you can call a tensor product category. You can take locally constant sheaves, and I explain what tensor product category means, with just our E vector spaces tensor the category of A modules. A was an E algebra. So let me just explain what I mean by tensor product of categories. So it takes place in Lewis' world of DJ categories, and it's designed in the following way. If you have two associative algebras, B1 and B2, so you can consider the corresponding categories of modules, and so the tensor product of categories of modules is designed so that it's the category of modules for the tensor product. And basically from this, you unspin the definition to give it in the general case. All right, so this is one context in which one knows how to define local systems. And again, I'll soon explain why such a definition doesn't work as is.
So the representation of the G hat, that's over the field E, right?
Yes, correct. So the Langlands dual group is over the field of coefficients.
Mm-hmm.
Always. All right. So here's another context in which one knows how to define local systems. This is the Durham context. So in this case, we work over some ground field K of characteristic 0, but in this case, the field of coefficients is the same K. So that's the kind of feature of the Durham situation. So let me say what Lox's Durham is. Well, it looks exactly the same as here, symmetric monoidal functors, blah, blah, blah. The difference here is that we put, instead of sheaves, we take D-modules. On X, again, tensor A mod. All right. So, but now we want to do it for l-adic sheaves. So here's the problem. If we look at the first definition in the Betti context, so what I said is that we are looking at locally constant sheaves of A modules. So the typical fiber of your sheaf is like A to the power n. And A is an arbitrary algebra over QL. So let's QL bar. So is commutative algebra over QL bar. Just think of like polynomial algebra in several variables. But the problem is that in the theory of l-adic sheaves, you're not allowed objects like this. Your l-adic sheaves, well, if you're talking about constructible sheaves, they're small. So they're built out of profinite sets. You cannot input there something infinite dimensional. So, and that is to say that there is no notion of a variation of l-adic sheaves over a kind of over a base, just exactly because, so our constant sheaf is QL, but you can take finitely many copies of it, but not going beyond. And so that has been the problem for decades, that people didn't know how to deform. So let me mention that. So recently, just a few months ago, Peter Scholze and independently Xinwen Zhu found a way to do it, and it at the end yields the same geometric object as in our paper. So by the way, I'm talking about the paper of 6 authors. It's Arinkin, so myself, Kazhdan, Raskin, Rosenblum, and Warshawski. So it's a paper that exists on the archive. All right. Nonetheless, I will now define a geometric object, which is what we'll call Loxist restricted. And its feature is that it actually exists in all sheaf-theoretic contexts. So it will exist in the Betti context, it will exist in the Durham context, it will exist for l-adic sheaves, and in the definition is uniform. However, in the Betti Durham context, it gives not the original Loxis. So it's the object that I'll call Loxis restricted. And so here I give the definition. So home from spec A. So, and again, emphasize you work in any sheaf-theoretic context you want. Loxis G-check restricted is, again, funct symmetric monoidal, just as before, from rep G-check. And what you do, well, you do basically the only thing that you can do. So I'll write and I'll explain. So I say lease of X tensor A mod. So where lease is, let me write it, the category of, well, finite dimensional local systems on X. So now let me go back. So, and you can do it in the Betti theory. And let me explain the difference between this Loxis restricted and Loxis Betti that we had before. So what will happen is that, so we'll have an
the
embedding.
Local systems are all l-adic local systems.
No, so this works in any sheaf-theoretic context. You can input your Betty sheaf theory, so you'll be working with
NAE.
It's any E, so any sheaf-theoretic context. In Betty, you'll be looking at just least local systems of E-vector spaces, of finite dimensional E-vector spaces. In the Betty context.
In the Durham case, I was not.
In the Durham case, it will be.
Has to be l-adic.
No, in the Durham setting, it will be. So what we call least is just least D-modules. These are D-modules that are vector bundles, finite dimensional vector bundles with connection. And in the l-adic, these are just least l-adic local systems as they are.
Because the D-module is over K.
Yeah, so it depends on, so as I said, in the Durham setting, E equals K.
Okay, thank you.
And so in the Betty setting, your K, so your ground field is C, if you wish, and the field coefficient is any E, and the l-adic setting, again, your ground field is anything, and E is QL bar.
Thank you.
Yeah, so in the Betty setting, we'll have an embedding, but it's not at all an isomorphism. And let me explain the difference. The difference is as follows. So let's, in the Betty setting, we could also think of local systems as, well, this homomorphism point of view. So it classifies homomorphisms from pi1 of x. Let me just say, so A points are well, if you choose a base point, you can say it like this. Let me explain for GLN so that we don't worry about rep G check. So for GLN, what we do, it's just actions. So of pi1 of x on just the free module of rank n over a. So it's actions of pi1 of x on a to the n. So that's that's what Loxis Betty classifies. And so Loxis restricted, it's the condition that this action is locally finite over k. So condition is that every vector, every element in AN is contained in a finite dimensional vector space over E stable invariant under the pi1 action. So it's a very strong condition. So it's kind of finite dimensionality over E. And what you'll see is as follows. So kind of algebra geometrically, again, still in the Betty context, it looks as follows. It's equals the disjoint union, let me call it, of formal completions of closed subsets, let me call it Y. Let me call it Y. I'll explain what Y is. It's certain closed subsets Y in Loxis Betty, where Y runs over the set of semi-simple local systems let me call it better, sorry, I call it sigma. so sigma runs over the set of semi-single local systems, and Y sigma is the closed subset in log sys with a given semi-simplification. So, in particular, all irreducible local systems sit separately, but you don't take them as points, you take them as fat points. You take the formal completions. That's kind of on one extreme. On the other hand, you can take the set of local systems whose semi-simplification is trivial, and it'll be a full dimensional variety, and still you full dimensional closed substack, and you take its formal completion. So that's how log sys restricted looks inside log sys Betty. And you have a similar situation in Durham. Again, log sys Durham exists, and so log sys restricted inside log sys Durham looks exactly the same way. It's also the disjoint union of formal completions of the loci with a given semi-simplification. And in general, so this is kind of, we can say what log sys restricted is in this case as a subset of something known. In the l-adic case, there is no ambient thing. There is just log sys restricted. And you can prove a theorem that, so this log sys restricted is a formal algebraic stack. So what this means is this, that in very concrete terms, so typical algebraic stack, you take an algebraic variety mod out by an action of a group. So in this case, so this means the following: it'll be no longer a variety, but it'll be a completion of a variety along a closed subset. So it has the form completion of a variety along a closed subset modulo an action of the group. So that's the algebra geometric nature of it. So it exists as an algebra geometric object, and finally, so we can do it again in any sheet theory, but now let's come back to the case where we work so over a field of positive characteristic, and we're assuming that X is defined over FQ, and in this case, by transport of structure, so this log sys carries an action with the Frobenius. So X itself, by virtue of being defined over FQ, carries what's called the geometric Frobenius. So it's a endomorphism of X over spec K, and it induces the transport of structure and automorphism, in fact, of the symmetric monoidal category of Lees sheaves, and therefore it induces an automorphism of our stack log sys restricted, and we define log sys arithmetic in this case as Frobenius fixed points. So this is the algebra geometric object that I said did not exist until about a year ago, and so it's in our approach. And as I said, Scholze and Zhu have a different approach, which constructs the same geometric object. But the theorem here is that.
Can I interrupt you?
Please.
Try to understand this Y sigma. You use the semi-simplification. So can I try to understand that? So in the conjugacy classes, they all have the same fixed the characteristic polynomials.
That's exactly the same. So,
okay.
That only exists in the Betty setting. So let me just so a tiny digression. So in the Betty setting, there is log sys. You check Betty, But there's also the coarse moduli space. Let me write it like this. Coarse moduli space. So the Betti stack is a quotient of an affine scheme by the action of G-check, and coarse moduli space is just the spectrum of the algebra of invariant functions. And so this coarse moduli space, its E points are exactly those sigmas, and let me call it R, and Y sigma is exactly the preimages of these points. That's what they are. Does it answer the question?
Yes, you did.
Yeah. All right. Yeah, indeed. But this picture only exists in the Betti setting. In the Durham setting, we don't have this picture. And yeah, but so you define Lox's arithmetic and just as Frobenius fixed points, but then one proves a theorem that this Lox's arithmetic is an actual algebraic stack. So it's not a very easy theorem. So as I said, restricted has all these formal directions, but the claim is that if you apply fixed points of the Frobenius eats up all these formal directions, and you're left with an actual algebraic stack. And moreover, so
Dennis, I'm a bit confused of infinite type.
Finite.
Finite, why?
So even Lox's restricted was what we call of finite. It's algebraic. It's a formal algebraic stack of locally finite type. And this one is, if it take Frobenius fixed points, it's locally finite type, but because algebraic.
Locally finite type.
It's locally finite type, but it has finite. It's as finite as you can wish. It has finitely many connected components, each of which is a quotient of like a affine scheme by G-check. It's finite.
Okay. Yeah. Sorry. Yeah, your G is fixed, is JLN. Yeah. Okay.
Well, G is any reductive group, but it's
it's fixed. I mean,
it is fixed. Yes.
Yeah. Okay.
The rank doesn't vary. So this is the main character. So we'll be studying the dualizing sheaf on it. So one can say something about infinitesimal properties of it. So
stupid question.
Please.
For Riemann surfaces and characteristic 0 and complex numbers, like, is it something new or?
So arithmetic is again arithmetic. It's
no, not arithmetic, but restricted.
Yeah, that's what I said. So it is new in the sense that nobody has considered it seriously. So namely, it's the following thing: you have the usual stack of Betti local systems as you know it, just homomorphisms from pi1 to G-check, modular conjugation, and there's the character variety that I call the coarse moduli space, and it's the disjoint union of formal completions of the fibers. So it looks kind of stupid, but as you'll see, it's not stupid.
Even in characteristics, even for Riemann surfaces. Yeah.
Well, as an algebraic geometric object, we'll soon see an application of it.
Okay.
So actually,
yeah.
you talk about Frobenius morphism on the local restricted.
Yes. Yeah. So Jan was asking the restricted guy.
Yes.
Yeah. So the arithmetic guy only exists over field of positive characteristic. So let me just mention one thing about kind of infinitesimal properties. So this Lox's restricted is what's called quasi-smooth. And what this means is that if you take derived tangent spaces of it at points, let's call sigma be just a field valued point, it lives, well, it's a stack, therefore, so let me say tangent space. So the tangent space has something cohomological degree -1 because to account for automorphisms. But so it lives in cohomological degrees from -1 to 1. So in general, a scheme is said to be quasi-smooth if its tangent spaces live in degrees 0 and 1. smooth is just 0. So this is restricted. And in the same way as kind of usual locus Betty and locus Durham. So this arithmetic guy is what one can call quasi-smooth. So they live in degrees from -1 to account for automorphism up to 2. And so as a corollary of this locus arithmetic is truly an object of derived algebraic geometry. So its structure sheaf has infinitely many, lives in infinitely many cohomological degrees. All right. Any more questions? So we'll now pass to the geometric story, just story with geometric Langlands. All right. So I'll now I'll remind you the statement of geometric Langlands conjecture in the context that it was known. So first, Durham context. So here we consider the derived category of D modules on bun G. So this is Durham. So our field of coefficients is the same as the ground field K. And yeah, somebody was saying something?
Yes.
Yeah?
Yes,
please.
you emphasized this because earlier I didn't catch it.
Say again?
The field K equals E in this case.
In Durham context, yes. So this is Durham. And so the naive version of the conjecture was that you could take quasi-coherent sheaves on the stack of Durham local systems. So this is not quite right. So it required a correction. So you have to do what's called int-coherent sheaves with also prescribed singular support. I don't want to go into these technicalities, but it's kind of important correction, which will ultimately account for this omega replacing O. So this is in the Durham theory. And this conjecture is essentially due to Beilinson and Drinfeld. It appeared informally in the 90s. So then David Bensby, David Nadler were wondering, so does this conjecture have an analog in the Betti context? So the right-hand side did have an immediate analog. So you take incoherent sheaves, nilpotent single support just on the Betti side. And again, so here, Betti, you are over complex numbers, and if our field of coefficients is anything. So the question is, what is the left-hand side? So then they looked at the case of the torus when G check is GM. So let me write it in the case of Picard. So in this case, this nilpotent singular support condition actually means that you're considering quasi-co. So it's log cis GM Betti. And in this case, it's kind of easy to see that, so Bun-G is Picard, but if you want an equivalence, you should not consider all sheaves on Picard. You really should consider locally constant sheaves. All right, Bun GM, which is just Picard. But it's locally constant sheaves, but not what I called lease. So these are locally constant sheaves with infinite dimensional fibers. So the monodromy, when it acts, doesn't have, well, it's not locally finite. And then, and then they proceeded. So this is, let me call this is Beilinson and Drinfeld. And this is, all right, it's Bensby Nadler. So they guessed what the answer should be. And the answer is remarkable. So what they said is that you have to consider, well, the geometric object is still Bun-G. You consider all topological sheaves. Let me call it, I'll write all to indicate that it's not constructible. So kind of infinite dimensional fibers. You consider all topological sheaves, but you impose the condition of what's called singular support. So if you have a manifold and you have a Lagrangian subset inside its cotangent bundle, you can, inside topological sheaves, sorry, all, you can single out the subcategory it's the work of Kashiwara and Shapira from the 80s, sheaves with singular support in M. So Shapira, sheaves and manifolds. And so, and this is what their guess was. So where nilp is in the cotangent bundle of Bunge, it's what's called the global nilpotent cone. So let me say what it is for GLN. For GLN, T star Bunge is the modular space of Higgs bundles. So these are just vector bundles M together with the Higgs field, which is a map M tensor one forms. And nilpotent cone is the condition that this map be nilpotent. So when you iterate it, you get a map from M to M tensor one forms to the power n, and for n large enough, it's supposed to go to 0. So that's what they guessed. So I want to emphasize that there's a subscript nilp on both sides. They plays a very different role. So in the left-hand side, it's singular support in the sense of topological sheaves, and the right-hand side is nilpotent in the sense of coherent sheaves. These are very different theories.
Denis, just
yes?
for my information, the generalization of Kashiwara-Shapira to stacks, it's straightforward.
It's straightforward because the condition is local and smooth topology. So,
yeah, okay.
Yeah. All right. So that's what has been known. But now we want to do it in the l-adic setting. And the question is what to do. And here is the kind of restricted version of the geometric Langlands conjecture. It's obtained by marrying those two. And this restricted version, like my Loxis restricted, makes sense in arbitrary theoretic context. It makes sense for Durham, Betty, and l-adic. So
for Betty, what you use this site a definition of singular support, something like Williamson site.
No, so for l-adic. So
yeah, for l-adic, yeah.
Yes, exactly. So
okay.
So the right-hand side is, so I take, so again, my ground field here is K, is algebraically closed. So I take Loxis restricted, just as we introduced it above. Sorry, check of X. And I take int co. It still makes sense because I mentioned Loxis restricted is quasi-smooth. So all of this makes sense. All right, and the left side is I call sheaves. And when I write sheaves, I mean constructible sheaves. So in the Betty context, I want to distinguish sheaves, what I call all and constructible. So these guys are really constructible. And in the Durham context, these will be holonomic D-modules. And it turned out that all these holonomic D-modules are automatically regular. It's actually a theorem. So on Bunge. So this is what we call the restricted version of geometric Langlands conjecture. And again, it makes sense in arbitrary sheaf theory. And so the remarkable thing is that, so this version of Langlands conjecture, in the Betty and Durham versions, it follows from the original versions when you have the entire Loxis, but there's a nice trick that allows to go the other way around. So in fact, this restricted version implies both other versions as well. So remarkably, this restricted version is equivalent to the original one.
Sorry for kind of...
No, please.
For Williamson and Greenfield's story, on the right-hand side for Durham Loxis, you have a restriction on the support, and on the left-hand side for the modules,
none.
And no restriction. Okay.
And here I require restricted single support, which forces, because this nilp is Lagrangian, it forces my D modules to be holonomic.
Yes.
and that's the conjecture. So as I wrote it, it literally makes sense in any of the contexts.
Okay.
So, all right. Okay. So, and now, so the last thing I would like to explain is I will explain how this conjecture implies that the isomorphism between the space of automorphic functions and global sections of the dualizing sheaf on arithmetic local systems. Omega, I always write omega for the dualizing sheaf. So it turns out that, so the geometric statement implies the statement on the level of functions. So for this, we'll need to review the notion of trace. So, well, we know what traces on vector spaces. If you have a finite dimensional vector space and you have an endomorphism, trace is a scalar that equals to the following thing. So we have vector space, we have the unit. It's mapped from, so my linear algebra is taking place over the field of coefficients E. So I write E. We have a unit map from E to V tensor V check. Then we apply our endomorphism along the first vector, and then we apply the pairing back to E. So we get a map from E to E, it's a scalar, and that's the trace. So that's just trace of T on V. So, but now this definition makes sense in an arbitrary symmetric monoidal category. Just apply the same thing. Instead of V, you take a dualizable object in your symmetric monoidal category. Instead of E, it's the unit object. So let me just say that if O is a symmetric monoidal category, and little o is a dualizable object, and T is an endomorphism of O, to this thing you can attach the trace of T on O, and that's an endomorphism of the unit object of the, all right. But so the context we're going to apply it to is when your O is the category of DG categories. And we already mentioned above the tensor product, it's this Lurie tensor product. And so I have to say a word what dualizable objects are. So in particular, so for DG categories, it makes sense to talk about compactly generated ones, and all of these guys are dualizable. So the unit object there is the DG category of vector spaces. So the upshot is that if you have a DG category, let me call it C, and an endofunctor T, you can attach to it its trace, let me call it categorical trace. And it's an endofunctor vect, but endofunctors of vect are vector spaces. So it's a vector space. So it's a kind of higher trace. The trace of an endofunctor in the category is a vector space, and it's otherwise known as Hochschild homology. It's TLS. So this is really not anything new. So now I would like to, in order to proceed further, I want to give a calculation of what it looks like in some example. So let my C be the category of quasi-coherent sheaves on some stack Y. And so let T be given by the direct image with respect to some endomorphism phi. So phi is an endomorphism of Y. So, and I would like to calculate the trace, and what I'll prove is that the trace of this functor on this category is global sections on the stack of phi fixed points on Y of the structure sheaf. So let me do the calculation. It's really fun. So remember, how a vector spaces, we had to know not only V, we had to know its dual. So the claim is that the dual of the category of quasi-coherent sheaves on Y is itself. So namely, well, you have to put some reasonable assumption on Y. So the key thing to know is that if you have two algebraic stacks Y1 and Y2, the tensor product of these categories easily follows from this kind of definition with algebras. It's actually quasi-coherent sheaves on the product. Remember, like if you have B1 modules, tensor B2 modules, it's the same as modules for B1 tensor B2. And for affine schemes, it just proves it. And for stacks, you need to do a little more work. So now I'll explain how this category of quasi-coherent sheaves on Y is self-dual. So namely, I'll explain the unit and co-unit map. So the co-unit map is as follows. So you, as I said, you identified with quasi-coherent sheaves on Y times Y, and then I have to map it to vect. And what you do is this: you pull back with respect to the diagonal to go quasi-coherent sheaves on Y, and then you push forward, just take global sections. So that's the co-unit, and the unit is as follows. So I need to map vect back to quasi-coherent sheaves on Y, tensor quasi-coherent sheaves on Y. So what I do, I map vect to quasi-coherent sheaves on Y. So namely, well, E goes to the structure sheaf. Then I apply the direct image. I go to quasi-coherent sheaves with respect to the diagonal, and then I identify again with respect to the product. Okay, so I've specified the unit and the co-unit, and now I'm in the position to calculate the trace. So let's apply our definition of trace. So what I'll do is this: I'll be pulling back with respect to maps that in my diagram will be vertical, and I'll be pushing forward with respect to horizontal maps. So what do? So we start with point, quasi-coherent sheaves on point is vect. We pull back to Y. Then we push forward with respect to the diagonal map. So we create our unit. Then we push forward with respect to phi tensor identity. So this, we are applying our functor. So then we pull back again with respect to the diagonal, and then we push forward to the point. So we have to chase through this diagram. We obtain a functor from sheaves on the point, which is vect, sheaves on the point, which is vect. And let's see what this functor is. Well, here I do push forward and pull back, but first of all, I have here a composition of push forwards, and the composite map is the graph of phi. So let me just modify this diagram, and I'll write this map as graph of phi. But now I do push forward and pull back, and I have base change. So, and the Cartesian product here is, so the fiber product here is just exactly fixed points. So I might as well I can pull back all the way to Y phi, and I push forward all the way to Y phi. When I pull back, well, and by definition, this gives me, so this map sends E to the structure sheaf, and this map is just take global sections. So I've proved, I calculated the trace to be global sections of the structure sheaf on fixed points. I want to see if people are still here. Jan, are you here?
Yeah, I'm here.
Yeah.
Yes, I'm also here, don't worry.
Almost everyone is here.
Yeah. So it just, all right.
I will try to make some noise, so we are here.
Yeah. So like I gave 2 talks already today. One was my class, and at some point I got disconnected, and I hadn't realized that it was like I was talking for like 5 minutes without into the void. All right. So the point I want to make is the following: that so we can try to do the same with l-adic sheaves. And so I want to calculate the trace. So again, I have Y, I have phi, think of the Frobenius. I want to calculate the trace of phi lower star on l-adic sheaves on Y. And I want to write the same calculation. So basically what I want to see, that it's going to be, well, kind of,
so it's
I'll
a
write
vector
gamma
space, which probably will be your atom or close to it.
Yeah. But so Y is arbitrary. So we'll write gamma, I mean global section. Let me say chains, co-chains. On fixed points, well, properly speaking, there should be dualizing sheaf here. But the problem is that you made kind of this calculation formally works apart from the following annoying place. So sheaves on Y1, tensor sheaves on Y2 maps fully faithfully to sheaves on y1 times y2, but this map is not at all an equivalence. So therefore, and so there is a map in one direction like this, but this map is not at all an isomorphism of vector spaces. So left-hand side is huge, and the right-hand side is much smaller. So, and we really want to apply it when y is defined over fq, and phi is the Frobenius. And the important observation here is Frobenius fixed points is what we call y of fq. And so if y was an algebraic stack, this is a discrete algebraic stack. This is really a disjoint union of isomorphism classes of fq points of y, of stacks of the form point modulo finite group, which is group of automorphisms of your y over fq. So in other words, this entity, y Frobenius, is what you meant, is really functions, in fact, with compact supports on y of fq, ql bar. So what I said here is that if you take the trace of the Frobenius, Frobenius push forward on sheaves on Bun-G, it has a map to functions, to automorphic functions, but this map is not at all an isomorphism. But so here comes, so what we call the conjecture, but since then we were able to prove it, you can do the following thing. So you have this category of all constructible sheaves, but then you have the subcategory of sheaves with important singular support, and you can consider decomposition. You can consider the trace not on the entire category of sheaves, but specifically on the subcategory of sheaves with important singular support. And it maps by the functoriality of the trace to the trace of the Frobenius in the entire category. And then you apply your, well, this local term map to go to autom. And the claim is that this composite map is actually an isomorphism. So it's a kind of interesting statement. It's maybe the first time that it's the first bridge between the geometric and the classical theory. So geometrically we consider some categories, and classical we consider some vector spaces. And what the theorem says that these vector spaces are in fact traces of the Frobenius, but you have to pick your category judiciously. It's not all sheaves, but it's really the subcategory of sheaves with important singular support. All right, so and now I'm ready to wrap up my talk. So I said that I wanted to explain how the geometric Langlands conjecture implies the classical Langlands conjecture. Well, we just said that on the geometric side, the space of automorphic functions is the categorical trace of the Frobenius on sheaves with important singular support. So to deduce the classical Langlands conjecture, all that remains to do is the following. So you have to consider trace, again, of Frobenius push forward on this category of incoherent sheaves with important singular support on log-cis restricted, you check X. And what you want to see is that this is global sections of arithmetic of omega. So the calculation that I did above proves exactly that, but if instead of incoherent sheaves, I have quasi-coherent sheaves, and then I get O. But then you can, well, it's not a huge deal, but you have to kind of unwind the definition of incoherent sheaves, and you'll see that if you modify your quasi-coherent sheaves to incoherent sheaves, the answer will be global sections of omega instead of O. And that's how you get this classical Langlands conjecture from the geometric one. And I guess that's my talk.
Thank you very much. Okay, questions, please.
And here, you're all everything is in the derived version or just on the concurrent?
Can you say one more time?
And here the osmosis is the coherence. This in the derived version or just simply on the shift level. Because I try to feel where the Lefschetz fixed theorem or the trace formula.
Just one second. So maybe let me go back to sharing. So maybe I should stop the share. Just 1 second. So
the trace should be alternating sums.
Yeah. So everything is derived here.
Okay, thank you.
Yeah. So yeah, that's easy to answer.
So, Denis, I have a question about your restricted version of GLC. I kind of missed it. It's still a conjecture, yeah?
It is a conjecture, yes. The same way as GLC is a conjecture.
Now, what is a functor? Is there a functor from one side to another, and what?
So there is. Let me just. You mean in the l-adic case, or in the Durham case, or the Betty case? So this
probably, I mean, Betty is kind of probably maybe it's the most topological, so it will be easy to understand. Although in the Durham probably it's something like Hickey.
So in the Durham setting, so I mean I have a paper where not even restricted, the entire thing, there's a functor in one direction, and
in that direction
there's a functor in this direction. There's an adjoint functor. I mean, we still can't quite prove that it's an equivalence, but it's kind of close. So, but in the Durham theory, there are more methods to prove such things than in the Betty and l-adic, namely because you can access demodulus and Bunge via localization at the critical level. So that this gives us extra tools to prove things. So in the other cases, there is a candidate for a functor in the same direction, but we don't know that. So you can characterize this functor in one direction uniquely, but we can't quite prove that it exists. Except in the case for GLN. For GLN, I think we can prove everything.
All right. So, but I'm not religious about an arbitrary G. So for GLN, what is the functor?
So I think that for GLN, so it's what I call a quasi-theorem. It's an unwritten theorem. It's still a lot of work to do, but I mean, all the ideas are there.
Morally, I mean, I'll explain you my interest in a moment. But what are the functors? So you have some shifts supported on some Lagrangian.
No. So
right?
No. Like, so
the left hand side.
So the functor goes from, it's singular support, right? It's not support.
Yeah, it's singular support. Yeah. It's singular support. So it's like
the functor goes from the right hand. So the functor goes from the right hand side to the left hand side, from the spectral side to the geometric side.
Okay.
So let me write a little bit. So here we have this int co. So, and you want to construct a functor to sheaves here. So, but what inside encode, you have the usual quasi-co. Encode is an enlargement. And, sorry, not Bunge, it's Loxis. Loxis restricted. Yeah, but so first you prove the following theorem. It's proved in our paper. Is that so? But note that quasi-co is a symmetric monoidal category, so it's compactly generated by perfect complexes. You can tensor those together, and you can act by them on int co. So you prove the following theorem. We call it spectral decomposition theorem. That this category actually, as a monoidal category, acts acts here. So like, and if you wish, this is kind of the first application Loxias restricted. So it says that like, even in the Betty case, Loxias restricted, well, it's kind of naive. It's really kind of this disjoint union of formal completions, but quasi-co on that acts on the category of sheaves on Banji with important single support. So if you want to construct a functor out of quasi-co, you have to, because it's a free module over itself, you have to specify one object. And this object is the following one. If you did not put the nilpotent condition, it will be what we call the first Whittaker coefficient, but otherwise you have to make it have nilpotent single support, and what you do is this. So we have so there's an embedding and there's a right adjoint. And so you take the first Whittaker coefficient, it's a particular object, and you apply this right adjoint to it. And that's the image of the structure sheaf on quasi-co. So that's what you do on quasi-co. Now, so then you have to extend it to int-co. So then you have to see how different is quasi-co from int-co. And there comes our paper with Dima Rinkin. So it explains that the difference comes from what we call Eisenstein series, from Levi subgroups from smaller rank. And so then you kind of, by induction on the semi-simple rank, you define the functor on those, and then you glue it together to a functor on the entire category.
And this nilpotency condition on the coherent side, is it possible to explain it kind of to unexperienced?
Yeah.
Persons?
Yeah. But by the way, I think, weren't you in my course at IHS when I did it?
Well, I was at IHS, but I'm not sure I attended your course, so
yeah,
kind
so
of F for me, but
yeah.
All right.
Yes.
So anyway.
Yeah, I'll explain. So okay, let me. Yeah, 1 second. So okay, so here is kind of the fastest definition. So Y is a, let's say, quasi-smooth, let's say scheme, it doesn't matter, it's a local definition. And let's say M is a coherent sheaf, really coherent. And to it, so now what's singular support? Where does it live? So to Y, you assign a following variety, kind of naively, it's the following thing. It's, well, you can think of the cotangent bundle as, union over points of cotangent spaces. Let me just, in the same language, say what sing is. It's union over points in Y of H minus 1 of cotangent spaces. So the fact that Y was quasi-smooth means that the cotangent spaces live in cohomological degrees 0 and -1. So, and I'm taking the kind of the total space of H minus 1s. It just measures how not smooth your Y is. So now to a coherent sheaf, you attach a singular support, which is in fact a closed subset inside the sing of Y. And it measures how far your M is from being perfect. And so, and here is the definition. So let me.
Oh, I see.
So let me.
Is that singular support is the same as microlocal support in the Kashivara-Shapiro?
No,
no.
It's
a coherent. It's entirely coherent definition.
It's a coherent story. It's
coherent because there is the constructor story, right?
Say again. Kashivara-Shapiro is constructible story.
Oh, I see. Okay, thank you.
Yeah. So let me say what it is. So basically, I'll say when a point Y, C belongs to the singular support. And so what we do is this. So let's denote by iota Y the embedding of my point. So I have my coherent complex. So when I write co, I mean complex. So I take I up a shriek of this M. So if M was perfect, it would sit in finely cohomological degrees. But now, we'll, okay, I'll say when C belongs there. All right, so now there's something that acts on it. So namely, it carries canonically an action of the following de-Lie algebra. So namely, if you have any variety, if you take its tangent space at some point, and if you shift it cohomologically by 1 to the right, it's canonically de-Lie algebra. And so, and this thing is a module for this de-Lie algebra. So, but now let's break it into cohomologies. So we can take the direct sum of HI, just very naively, cohomologies of this thing, and it will be acted on by the GUR of this algebra. And so, well, yeah, so what do I want to say? So what I want to say is that it's, in particular, it will be acted on by the symmetric algebra on H2 of my tangent spaces. Sorry, H1 of my tangent spaces. It's with a shift, shifted cohomologically by 2 units. So what we'll see is that this cohomology of the cofiber is a module, just as a graded module of a graded algebra, and I can take its support. So now take its support. It's support, and so it is a conical subset inside the dual vector space to this, which is exactly my H minus 1 inside H minus 1 of the tangent, of the cotangent. So in other words, you are taking support with respect to the cohomological operations. And so this is singular support. So, and again,
so your YC does not belong to a singular.
So C is an element in this H minus 1 cotangent.
Okay.
So I'm saying that C belongs if and only if my C is in the support of this guy.
Mm-hmm.
So, and again, if M was perfect, perfect means that this kind of I per chic Y is finite dimensional. It means that its set theoretic support is 0. The singular support is a zero section if and only if the guy was perfect.
Yeah, I understand this definition is analogous. Yeah, it's kind of interesting. Your left-hand side of your restricted GLC, I mean, it's a category of some constructible sheaves with prescribed singular support on the stack. Yeah, but
yes,
since it's an M seminar, so some people are interested in mirror symmetry and things like Fukaya category, and the same Nadler long ago wrote a paper not on the stack level but the level of cotangent bundles to the manifold, where he explained that this kind of categories of sheaves, they define objects in some Fukaya category. Like constructible sheaves on the cotangent bundles, it's the same as physicists would call it A-branes, yeah, like Lagrangians, and even you can drop the condition that they are conical. Which means that instead of D modules on a space or on a stack like band G, you would consider like symplectic stack, I don't know, some and consider like DQ modules, which actually go back to the same Kashiwara and the same Shapira, but maybe the later time. So I'm just curious whether anyone tried to make sense on this side of GLC, just trying to work out what's upgrade of the Floer theory.
So I don't know. It's kind of.
I mean, it's not. I understand you are an algebraic geometer, but at least you are.
I'm not a Fukaya person, but I mean, so yeah.
But since you probably read Nadler, whatever did he mention?
So Nadler is aware of this work. I mean, one should really kind of approach Nadler with this, because I'm just not a Fukaya guy.
Yeah, I understand, but so I can kind of return to you. I am not entirely a Langlands person.
Yeah. No, but Nadler is both. So
yeah, okay. Yeah.
Just need to kidnap him.
Yeah, probably. More questions?
How about the relative Langlands?
You mean with spherical varieties? So far, no comments. No. So we, no. I mean, one should do it. I mean, we haven't gotten around to it yet.
Hello, sir. Can you tell me which people can find the singular support definition?
Coherent singular support?
Yeah, what's the paper?
You mean coherent singular support? Yes.
Yeah.
It's a paper of Dima Rinkin and myself. It's called Singular Support of Coherent Sheaves something.
Okay, thank you.
It's the year, I think, 2013 or something like that, or 14.
Okay.
Yeah, actually, Rinkin gave a talk about that, but probably it was too long ago to remember.
So there could be a big.
Oops. Hello.
Yeah.
Yeah. No, it was cut.
Probably it's internet problems. So Zhongzhu maybe was disconnected. Zhongzhu, are you here? No. Okay.
So, do you want notes of this talk? Do you want me to email them to you?
Yes. I would appreciate. Yeah.
I'll
also, you can. I mean, all right. People will find your paper. I have already found it with 5 authors. It's like 206. No, altogether 6, including you.
Yes.
Yeah, but without you, with 5 other people, 225 pages of exciting reading. So.
Oh my God, I'm sorry.
Yeah. All right. So you are not.
So yeah, it's only during COVID one can do such a thing.
150 slides.
No. Some people can write paper even longer without any COVID. Like you mentioned, Luri. Yeah. And
yes.
And also there is Machizuki, also a guy who writes. All right, Zhongzhu, you were disconnected. Do you still have a question?
No, I guess still can't hear me, right?
Yeah, now we do. All right, so last chance to ask Denise something.
All right, thank you so much for the invitation. It was fun.
Yeah, and thank you for giving a very interesting talk. And please email me the notes.